plus 1. Yeah, exactly. None. So there's no integers that satisfy this, so there are no elements in this set. So this is a fancy way of writing the empty set. Make sense? Cool.
I also have a question about um, the section 1.2 question number 8. I tried to solve it and I have a question. So for instance, for A, we need to set it up evening students. So how we can to set it up? In I tried. Should we use no for D actually they graduate non-math students. Should we use union symbol? I mean
So yeah, like day graduate non-mathematics. So you've got these groups that were defined in the previous problem. So D is the set of day students, G is the graduate students, M is the math students. So for somebody to be a day graduate non-mathematical major, they would be in the set D because they're day, they'd be in the set G because they're graduate, and they would not be in the set M. In other words, they would be in the complement of M because they're non-math majors. And so we're looking for the size of the set D union G union not M.
yeah, I got you. Thank you.
Okay, yeah, you're welcome. All right, and just to confirm, you can see my screen with my hand and my textbook page and all that. Give me a thumbs up, let me know. Cool, thank you. Normally Zoom puts a little green border around whatever window I'm sharing, and for some reason today, it's not giving me my little green border. So kind of going on faith. All right, good. Other questions on homework or material? All right, well, propositional logic. So we're going to spend probably a week and a half, maybe the next 2 weeks, talking about propositional logic, getting through some definitions, some core concepts, doing some work with different kinds of propositions, what we mean by a proposition, how we put propositions together, doing some initial proofs involving propositions. And then we're going to leave this topic for a while, go on to something else, and then come back to propositional logic. This is one of those topics that takes some time to sort of like settle in our brains usually. And so we can give the definitions and go through some examples, but to really kind of conceptualize what's going on sometimes takes some distance. Sometimes we need to step away from this. So we'll break this topic up into two pieces, but we'll come back to it again and again throughout the course, because it's a useful way to think about a lot of the things that we're going to do. So if we're talking about propositional logic, we have to figure out what a proposition is. So I'm going to give you a definition. And it's a pretty simple definition, but it's really critical. Every piece of it is important here. Um, and we'll say why in a little bit. So a proposition is a declarative statement that is true or false. So it's a statement that makes a declaration. It states something, and that something is either true or false. So, for example, my name is Nick. That's a declaration. It happens to be true if I'm the one making that statement. Um, X plus 1 is bigger than X. That's a proposition. X squared equals X cubed. That's a proposition. It may not be true. It's true if X is 1 or 0, but it's not true if X is equal to 2. So these are declarations. Some things that are not propositions. X plus 1 squared is not a proposition. It's an arithmetic expression. It represents whatever the value of X is plus 1 multiplied by itself, but it's not something with a truth value. You can't say this is true or false. It's not asserting anything. So it's not a declarative statement. Um, Goodbye is not a declaration. Why am I here is not a declarative statement. I am here because I'm taking CSE 215. That's a proposition. You got the idea? Got to be declarative. And that's pretty easy to understand probably, but when we're writing proofs, and as we write proofs, every statement we write will be a proposition. Sometimes instead of writing propositions, we may find we start writing things like x plus 1 squared or x squared plus 2x plus 3. And we've got to remember that's not a proposition. So I'll come back and revisit this as we continue using propositions as we start to get into proofs and such. All right, so a propositional variable is just a letter that represents a proposition. All right, when we're talking about, let's see, so I'm leaving would be a proposition. Yes, goodbye would not. Perfect. All right, so I might use the variable p to represent the proposition, my name is Nick. So here's how I want you to do this in this course. It's a little longer, a little more writing, but it's worth the extra effort. So I would say, for example, let P be the proposition, quote, my name is Nick. If you put this on your homework, your exam, whatever, there's no ambiguity here. It's absolutely clear. P is a propositional variable. It represents the proposition, my name is Nick. So that's good. Go ahead and do that. What I don't want you to do, so I'll say no, is something like P equals my name is Nick. Don't write that. There's a number of problems with this. Number one, are we saying that P is the propositional variable whose value is this? Or are we making an assertion that P is equal to this? In other words, is it a double equal sign in C or a single equal sign for assignment? Number two, we have propositions like x plus 1 is bigger than x. If I write P equals X plus 1 is bigger than X, is P equal to X plus 1, and I'm making a proposition that that's bigger than X, or is this the proposition and P is equal to that? And these might seem like silly, needlessly complex examples, but these are going to pop up. We're going to be doing a lot of proofs that involve having you create propositions and define propositional variables. And a lot of our proofs are going to involve arithmetic symbols. So don't do this. Don't do this. Instead, do something like let, R be the proposition X plus 1 is bigger than X, or whatever the proposition says. That's just a picky detail. I'll remind you if you start doing this to do this instead. And there's two propositions. They're propositions or propositional variables that are well defined and that we're just going to assume are always have this meaning. This is T and F. T is basically the proposition true, F is the proposition false. And in English, we can make a complete sentence by just saying true or false, right? That is a declaration. It's in some sense the ultimate declaration. So we're going to consider true to be a proposition that is always true, or T, and F or false to be a proposition that's always false. So we've always got those truth values. So question, how old is this study of propositional logic? Where do you think it started? Any ideas, guesses? So this actually goes back to at least 300 BC. And Aristotle studied this propositional calculus um, as a way to try to understand logic and reasoning and how we think as humans, how we come to conclusions in the way we do, and is there a way to formalize that? Um, George Boole in the 1800s visited this in a mathematical sense, what we now call Boolean algebra, again, as a way to sort of understand logical reasoning, how certain things follow from certain other things. And Boolean algebra, of course, is, the foundation of what we do in CSE 250, right? When we study digital logic, that's all Boolean algebra. It's related to propositional logic. Um, so you'll see some crossovers, and I'll point some out as we go. Um, so as with set theory, as with other things we'll be talking about, we're going to spend some time making new propositions from old ones. So if you have a proposition or a set of propositions, how can we come up with new propositions based on those? And so there's different operations we can do on propositions. So for the next, I don't know, few minutes, let P and Q be propositions. So they're symbols that represent declarative statements. The important thing is it doesn't matter what propositions these are. They're just any propositions, but the things we're going to develop right now apply regardless of what the actual proposition is. So our first way to make a new proposition is this, what's called a hook. So if we put a hook in front of a proposition, this is called the negation of P. And it's a new proposition. It's a proposition that basically says not P. So if P is the proposition, then my name is Nick. Then not P is the proposition, my name is not Nick. Technically, it's the proposition, not my name is Nick, but that's not how we speak. So to say not my name is Nick, we would say my name is not Nick. My name is something other than Nick. So that's one way to make a new proposition is to negate it. And if we want to understand what that negation does to a proposition, we can make what's called a truth table. So if we have a proposition P, it's a declarative statement which has a truth value. It's either false or true. And we can indicate that the negation of P will be true if P is false and false if P is true. So we get our familiar inverter truth table from CSE 250. All right, so that's the negation. Next operation, so we can call this a caret. So P caret Q, this is the conjunction of P and Q. And conjunction is basically an and operation. So this is a proposition. It's a proposition that's true exactly when P and Q are both true. So just to put some examples in here, let P be the proposition. My name is Nick. Let Q be the proposition. Today is Monday. So this is a third proposition. It's the proposition that my name is Nick and today is Monday. And we can make a truth table for conjunction because whatever propositions P and Q are, they might both be false or one might be true or they might both be true. And for each of those four cases, we can explain what the conjunction of P and Q would be. And it's false in all cases except this last case where both P and Q are true. And then there's what's called a V sometimes. This is the disjunction of P and Q. And this is like an or. So the disjunction is true if either or both of P and Q are true. And so we can add that to our truth table. And it looks like that. So just engineering 250, CSE 250, right? So there's also an exclusive or, and we don't have a fancy sounding word for that. But it's like a disjunction, but P and Q are not both allowed to be true. So it looks like disjunction, except if both P and Q are true, then the XOR is false. So my name is Nick. XOR today is Monday. It turns out to be false because both of these things are true. We don't use XORs a lot in what we're going to develop here, but it's a valid logic operation. This is a good time to point out that English is an imprecise language. and this course is taught in English, which means we're using an imprecise language to describe something that's very rigorous, something which has very precisely controlled interpretations. And there's a conflict between those sometimes. And we'll see this sometimes in trying to define something because we're defining something very precise using an imprecise language like English or any human language. Sometimes there may be a question that, is written in a human language like English, and it may not be clear exactly what the question is asking. There may be some ambiguity. The reason we have things like propositional logic and we're defining these symbols to mean certain operations and so on is to try to get away from that imprecision, right? If we're trying to understand how thinking works, how we process thoughts logically, how we come to conclusions, we need to be working with a very precise system. So we take this symbolic approach. But just a heads up, there's going to be times where things sort of go against what we're used um, to saying or thinking about when we hear something. So we'll keep an eye out for that. Um, all right. So, and if there's questions, just go ahead and shout them out on the way. Otherwise, I'm just going to keep going. Um, so conditional statements. So a conditional statement, again, P and Q are just propositions. Conditional statement looks like this. P arrow Q. And we would say that as if P, then Q. If we wanted to spell out the proposition. So again, thinking of P is the proposition, my name is Nick. Q is the proposition, today is Monday. This proposition says, if my name is Nick, then today is Monday. Kind of a weird statement. But if you want to translate this into words, just put an if P, then Q. It's exactly what it means. P we call the hypothesis. And Q we call the conclusion. Because we'll talk about those pieces a fair amount. And this idea of if P then Q, this is where we can get into some funny business with language. Um, Sometimes we might say if P, comma, Q, and that means the same thing. If it starts to rain, I'm going inside. Well, what we really mean by that is if it starts to rain, then I'm going inside. Well, we don't always say then. We might just say, if it starts raining, I'm going inside. So we might just say if P, comma, Q. We could say P is sufficient for Q. We don't always, we don't usually write things like that or say things like that, but P is sufficient for Q, meaning that, if P happens, that's it. That's all we need. Q is going to happen. We might say Q if P. I'm going inside if it starts raining. Well, that's uh, fairly understandable. Q follows from P. And so on. So there's different ways that you'll see this written. Um, But the base way to think of this kind of conditional statement, if P, then Q. And then if we have some other wording, we want to try to translate it into this conditional notation. All right, so P and Q are propositions. This is a new proposition. This is a declarative statement. It has a truth value. If we have this proposition, if P then Q, we can define three other propositions related to this. We can define something called the converse. And the converse is the proposition if Q, then P. The inverse is the proposition if not P, then not Q. And the third proposition we can derive is called the contrapositive, which says if not Q, then not P. So let's pick some sample propositions. Let P be the proposition. Today is Monday. And let Q be the proposition. We have CSE 215 today. All right, P is the proposition. Today is Monday. Q is the proposition. We have CSE 215 today. So this proposition says if P, then Q. If today is Monday, then we have CSE 215 today. Is that a true proposition? Just right now. Yeah, not on next week, but today, this is a true proposition. If today is Monday, then we have CSE 215 today. Okay, what does the converse say in words?
If we have CSE 215 today, then today is Monday.
Perfect, thank you. The converse says if we have CSE 215 today, then today is Monday. Now, is that a true proposition? Yeah, I mean it happens to be true today because today is Monday, but in 2 days, if I asked you again, is that a true proposition? The answer is going to be no, because today's not going to be Monday, but we still have CSE 215. So that can be false, even though this original proposition is true. All right, what does the inverse say?
If today isn't Monday, we don't have CSE 215.
Perfect. If today isn't Monday, then we do not have CSE 215. And is that true or false?
False.
That's false because, on Wednesday, it won't be Monday, but we'll still have CSE 215. All right, last one, contrapositive. This says if we don't have CSE 215, then today is not Monday. That's a lot of negatives to grok. If we don't have CSE 215, then today is not Monday. And under normal circumstances, right, other than holidays, that's a true proposition. If we don't have CSE 215, it can't be Monday, because if it's Monday, we've got CSE 215. So this actually turns out to be true. So the punchline here is that this proposition is not the same proposition as this. It can't be, because I can find particular values for P and Q where this is true, but this is false. And this original proposition is also not the same as the inverse, because I can find values where this is true, but the inverse is false. So the converse and the inverse are not the same as the original proposition. But it turns out that the original proposition and the converse always have the same truth value. They're either both true or they're both false. So I'm going to write a statement here. I'm going to write a triple equal sign. And this is a symbol for equivalent. And two propositions are equivalent if they always have the same truth value. And so it turns out a conditional statement is equivalent to its contrapositive, but not equivalent to its converse or its inverse. All right, good so far? Awesome. So let's look at the truth table for a conditional statement. All right. If P, then Q. Suppose that P is a true proposition and Q is also a true proposition. Is it true that if P, then Q? Yeah, that's a pretty easy one. So let's stick with the same propositions. P is the proposition, today is Monday. And Q is the proposition, we have CSE 215 today. All right, well, if today is Monday and we have CSE 215 today, then this conditional statement is definitely true. And this previous row is pretty simple. Suppose today is Monday, but we don't have CSE 215, then this conditional statement is absolutely false. Because this says if today's Monday, then Q should be true. And if there's a case where today's Monday but Q is false, this conditional is false. So those two rows are pretty straightforward to fill in. These first two rows are a little trickier. Suppose it's true that if today is Monday, we have CSE 215 today. Forget about holidays, forget about the end of the term. This is just a fact of the universe. If today's Monday, we have CSE 215. Suppose today is not Monday, but we still have CSE 215. Does that invalidate this proposition, or is this proposition still true? It's not Monday, but we still have CSE 215. Is that okay?
No.
Because I mean, like Wednesday, for example, P will be false. Today will not be Monday, but we'll still have CSE 215. So on Wednesdays, we have class. Does that invalidate the fact that if today is Monday, we have class? And it doesn't, right? It's not saying it's only on Mondays that we have 215. This is saying if it's Monday, we've got class. Well, if it's not Monday, this makes no claim whether we have class or not. So on Wednesday, for example, it's not Monday, but we have class. That doesn't make this proposition false. So this proposition is still true. And on Tuesday, it's not Monday and we don't have class. Well, that doesn't change the truth value of this proposition. So this still turns out to be true. But these first two rows can feel quirky. So let me try a different pair of propositions and see if we can at least make enough peace with this um to play around with it. So let P be the proposition. Um, X is bigger than 100. And let Q be the proposition. X is bigger than 5. All right, so depending on what the value of X is, P could be true or false, Q could be true or false. So suppose X is equal to 1,000. First of all, do we think that this is true? If X is bigger than 100, is X bigger than 5? Is that a true statement? If X is bigger than 100, then X is bigger than 5. Absolutely. That's just how numbers work, right? So we expect that this is going to be a true proposition. Okay, so let's pick some values. Suppose X is equal to 1,000. Is 1,000 bigger than 100? Yes. And is 1,000 bigger than 5? Yes. So if X is 1,000, we're in this case here where P is true and Q is true. And so if P then Q, well, that's true. What if I pick X equal to 0? So is P true or false? X equals 0.
False.
P is false. And what about Q?
False.
Q is false because 0 is not bigger than 5. So if X is equal to 0, I'm thinking about this first row of my truth table. The fact that I happen to think of an X value of 0 does not suddenly mean that this proposition is false. It's still true that if X was bigger than 100, it would be bigger than 5. X happens to be 0, so this is not true and that's not true, but this is still a true proposition. It's still the case that if X is bigger than 100, then X is bigger than 5. So this has got to be a true here. And if I set X equal to 10, well, is X bigger than 100? No, so P is still false. But is X bigger than 5? Yes, so Q is true. So if X is equal to 10, I'm thinking about the second row. P is false, Q is true. But it's still true that if X is bigger than 100, X is bigger than 5. So this is still a true proposition. Now, if I picked a value of X where this was true and this was false, I'd have a problem. But here's the question. Is there a value of X corresponding to this row? Can I find a number X that's bigger than 100, but not bigger than 5? Right? I can't do that. If it's bigger than 100, it's got to be bigger than 5. That's what this proposition actually says. So if I found a number that was bigger than 100, but was not bigger than 5, then this P implies Q would be false. Exactly because P implies Q says if X is bigger than 100, X is bigger than 5. So that's a specific pair of propositions that can kind of help us make peace with this kind of quirky truth table that a conditional statement has. So a conditional statement is always true, except in this one case where the hypothesis is true and the conclusion is false. So if P, then Q is true, except when P is true and Q is false. So here is a true proposition. If my name is Mary, then 1 plus 1 equals 3. That is a true proposition under propositional logic. And it's true because the hypothesis is false. The fact that the conclusion is false doesn't make this proposition false. This proposition is true. It's exactly this first row in the truth table. So we can write statements like this, and we can say this conditional statement is true, even though it's nonsense. So we'll be playing around with that later too. All right, so there's a biconditional. And we write a biconditional as a double-headed arrow. And this means if P, then Q, and if Q, then P. So the arrow goes in both directions. We can also phrase this as Q if and only if P. So Q if P, right? That's the arrow going that way. And Q only if P, that's the arrow going the other direction. It says if Q is true, then P has to be true. And this if and only if, you'll sometimes see that written as IFF, if and only if. We could say Q if and only if P. And we can make a truth table for that. And we can make the truth table directly from this definition. So if P then Q, remember, is true in all cases except this one where the hypothesis is it's true in all cases except where the hypothesis is true and the conclusion is false. So that's if P, then Q. And then if Q, then P will be true in all cases except where Q is true and P is false. And so if we take the AND of those, which is this biconditional, we'll just take the AND of these two columns. This is true, false, false, true. So the biconditional is basically saying that P and Q are equal to each other. And that's one way we can think of this. It means P and Q are either both true or both false. They have the same value. It's also the opposite of an exclusive OR. I don't know why. Think about that. All right, so this is all CSE 250 in different clothing, right? We've studied truth tables and Boolean algebra and things like that. But in 250, we don't really talk about conditional statements so much, and we don't talk about biconditional statements and so on. So we're kind of branching off in a different direction. Um, but there's some similarities and overlaps. So let's look at propositional equivalences. So we have a proposition P, and we can make a new proposition, which is the negation of P or not P. Suppose I do the disjunction of P with not P. So P or not P. Can we say anything about the truth value of this proposition?
It's always true.
It's always true. I mean, we can pick, if P is a proposition, my name is Nick, or my name is not Nick. That feels like it's always true. Turns out, no matter what the value of the proposition P is, this statement is always true. So we could say this is logically equivalent to true. And P and not P, that's going to turn out to be logically equivalent to false. So a proposition that's logically equivalent to true, we call that a tautology. A tautology is a proposition that's always true. And a proposition that's always false, we call that a contradiction. So a tautology is a proposition that's always true. A contradiction is a proposition that's always false. Anything else like P or Q, well, it could be true, it could be false. It depends on the values of P and Q. It's contingent on the values of P and Q. We call this a contingency. So tautology is logically equivalent to true. Contradiction is logically equivalent to false. Contingency is anything else. Could be true, could be false. Depends on the particular values of the variables. So when we're studying propositions and we want to know, is this proposition equivalent to true or false, or is it equivalent to something else? We can use truth tables, just like in CSE 250. So for example, let's show that this proposition, if P then Q, I'm going to add extra parentheses just for clarity, show that this is logically equivalent to not P or Q. And we can do this pretty mechanically. So I know what the truth table for our conditional statement is. This is true, true, false, true. And then I can make a truth table for this other expression. And like in 250, we're going to do this in pieces. First, I'm going to make a truth table just for the negation of P. So if P is false, the negation is true. If P is true, the negation is false. And then I'll make a column for negation of P or Q. And this proposition is true when either this or this is true. So if not P is true, then the disjunction is true. And if Q is true, which is in the second and fourth rows, then the disjunction is true. But in this third row, not P is false, Q is false, so the disjunction is false. So very mechanically, we can fill in truth values for this expression and this expression, and then we make the observation that these two columns always have the same truth value. Regardless of what P and Q are, these will both be true or they'll both be false. And that's our definition of saying that this proposition is equivalent to that proposition. It means they're both true or they're both false. So that's a mechanical way to use a truth table to prove that this is logically equivalent to that. And we can do that with all kinds of things. All right, so let's take a short break. And if you have access to your textbook, go ahead and pull that up because we're going to be looking at pages 50 and 51, mostly page 50. So you might want that around to refer to. But let's go ahead and take 5 minutes and we'll come back and we'll look at some identities on propositions. All right, I'm back. So let's look at some other identities, some other equivalences um, between propositions. So again, we're just going to assume P and Q are propositions throughout all of this. So if I take P and I AND it with true, what do I end up with? So P is some proposition. What do I get if I AND P with true?
P.
You just get P. Because this proposition will be true exactly when P is true and when true is true. Well, true is always true. That's what it means to be true. So this proposition is true exactly when P is true. That's what it means to say this is logically equivalent to P. What about the disjunction of P with false, P or false? So this is true exactly if P is true or if false is true. Well, false is never true. So this will be true exactly when P is true. So this is also logically equivalent to P. And this is called the identity property. If we do P and with false, well, false is never true. So this is equivalent to false. And if we do P or true, well, true is always true. So this is logically equivalent to true. And that's called domination. And if we take P or P, that's equivalent to P. We put P and P over here. So P and P is equivalent to P, and P or P is equivalent to P. And that's called idempotence. And if we have the negation of P, that's logically equivalent to P. That's called double negation. And we have all the usual suspects. P and Q is equivalent to Q and P. And P or Q is equivalent to Q or P. That's commutivity. And if we throw in another proposition like R, we can do things in a different order. You do Q and R and then AND that with P, and that's the same as doing P and Q and then ANDing with R. And the same thing with disjunction. So that's associativity. And so page 50 in your text, the main text, we have all of these laws. And this is very much engineering CSE 250. So the textbook uses 0 for false and 1 for true. conveniently sometimes. So I wrote P or false is equivalent to P. The book writes P or 0 is equivalent to P. They also use this double arrow, right? So two lines going in both directions. They use that for logical equivalence. I'm using a triple equal sign. So there's variation in notation. 0 for false, 1 for true, and so on. So we have De Morgan's laws. The negation of the disjunction is the same as the conjunction of the negations, and vice versa. Double negation they call the involution law. So if you're going to print out one page from your textbook, I would print out page 50. It's the page we're going to use the most out of the entire text, and we're going to rely on it for a lot of what we do with proofs, especially this second table down here. These absorption laws are useful. P and P or Q is equivalent to P, and P or P and Q is equivalent to P. And if you think about this logically, no pun intended, what does this left side say? Well, this left side is going to be true in the following case. P is true, and either P or Q is true. Well, if this left side is true, we know that both of these things are true, which tells us P is true. So if this left side is true, then the right side is true. On the other hand, if the right side is true, P, then we know this is true, and we know that this is true, and so we know that this whole thing is true. So P implies this. So the left side implies the right, and the right side implies the left. That's that biconditional equivalence. So it can make sense logically if we think about it. But we could also make a truth table. And a truth table will easily show that this has the same truth table values as just P. So truth tables are a mechanical way to show logical equivalence, but it's not the only way. Truth tables work well for computers, right? Because they're very sort of mechanical, and they can chew on these things. Put this up here. But there's other ways to do this. Here we go. All right, so let's do an example. Let's prove the following. The negation of P or not P and Q. That's a not symbol. Is logically equivalent to not P and not Q. All right, we'd like to prove that this is true. And we'd like to do it using some set of laws that we know. So if we can start with this expression and show that it's equivalent to something else, and that's equivalent to something else, and eventually show that it's equivalent to this, that will convince us that this is equivalent to that. So here's a first version of a proof. Can we find something that this is equivalent to just by using one of these laws up here one time? Do any of those laws apply to this expression? So let me take a sidebar here. Talk about boxes and circles. So let's pick one of these expressions. Let's just play with absorption. So we have a law which says P or P and P or Q is logically equivalent to P. So P and Q are just placeholders. They're propositional variables. They could represent any proposition. But when we see the letter P, we think that's the proposition P. And if I had some expression involving not P, I might not be sure what to do with this. So let me rewrite this in a different way. Instead of using letters as placeholders for propositions, let me write a box. I'm going to say box ANDed with box or circle is logically equivalent to box. Okay, this is the same statement as that. It's still this absorption law. But by getting rid of the P's and Q's, it makes it easier sometimes to apply this identity to other expressions. For example, from here, I could fill in the box with, let me do this in pencil. I could fill in the box with not S. And I could fill in the circle with R. And now this tells me not S ANDed with not S or R is logically equivalent to not S. That's just the absorption law. It's this thing right here. But I let P be this other proposition, not S. Or I could fill in the box with P and Q. And I could fill in the circle with not Q. And that gives me the identity P and Q and P and Q or not Q is logically equivalent to P and Q. So what am I doing here? I'm just playing with this one identity, but I'm not thinking of this as just the proposition P. I'm thinking of it as a placeholder, a box that I can put anything in that I want as long as I put that same thing here and here. That making sense? So when you're working with these identities, these laws of logic, you don't have to have a P and a not P to apply this negation law. It could be A or B or C and not A or B or C, and that's going to be equivalent to 0 or false. So keeping that in mind, this expression here on the left, not P or, not P and Q, can I write that as equivalent to something else using one of these laws of logic? So you're trying to match the form of one of these laws as opposed to the particular letters. P or P and Q is equivalent to P. So let's try that. So P or P and Q is equivalent to P. So something ORed with the same something and something else is equivalent to that first something. So that's really, really close. I can almost take this expression and fit it into that form because I've got a P, I've got an OR, but I have a not P here, and then I have a Q over here, and I've got this extra not in the front. So I think I'm going to be able to use that with a bit of extra steps first. But right now, that doesn't exactly fit into that form, but it's close. Is there a different form in here? One of these that might fit this. So this is not algorithmic, right? There's no set of steps you follow and you get the answer at the end. This is an exploration of possibilities. And the exhaustive way would be to take each of these laws and think of it as, box or circle, box or circle or a triangle, box and circle or a triangle, right? And seeing if for any of those you can fit this into that shape. And the first few times we do this, it's going to take a lot of trial and error. But as we do this more, our brains figure things out. Our brains start to rewire parts of itself, and we will be more efficient at finding things that fit this pattern. So let's take a look at De Morgan's law. De Morgan's law says not, parentheses, box or circle is equivalent to not box or, sorry, and not circle. So that's this first version of De Morgan's law. And if I look at this left side, well, I've got a negation symbol on both. I've got an or here. I could put a P into here. And in the circle, I could put, I need more space. In the circle, I could put not P and Q. And if I do that, now this exactly matches that form. right? Not parentheses P or not P and Q. Does everybody see that? So De Morgan's law says this is equivalent to this. It's equivalent to not whatever goes in the box, which is P, ended with not whatever went in the circle, which was not P and Q. So I can use De Morgan's law. And absolutely airtight, I can claim that this is equivalent to that. All right, I'd like to find another equivalence. Is there some way I can take this proposition, or maybe a piece of it, and change it into something else using one of these laws of logic?
Double negation.
Double negation. So double negation involution says not P is equivalent to P. So not something is equivalent to something. And I can put anything I want in here as long as I put it over there too. So the P right here might look like a not P, like a double negation. But if I put a P in here, I've got not P. That's different from not parentheses, not P and Q. And if I did something like not P and Q, that doesn't quite fit into the form of this. This says I need to be negating the negation of something, anything. But here I'm negating not a negation, but an and, a conjunction of two things. So that's close, but it doesn't quite fit the form. But there is something else in here that will. And it's on this side where you were looking. Other ideas?
I don't know if I'm right, but kind of like looks like the right side of De Morgan's theorem, something like that.
Yeah, right. We've got a negation of something anded with something. That's De Morgan's negation of something anded with something. So that should work really well. So let me rewrite De Morgan's. It actually says not P and Q is equivalent to not P or not Q. But if we get rid of the P's and Q's, let's think of this as not box and triangle is equivalent to not box or not triangle. So there's De Morgan's law. And this part over here, we've got a negation of something ANDed with something. So if I put a not P in the box and I put a Q in the triangle, this left side of De Morgan's law is exactly this expression right here. Not parentheses, not P and Q. So this whole proposition on the right should be equivalent to not P ANDed with, and I'm just going to replace this with what De Morgan's law says it's equivalent to, which is not P or not Q. And it's De Morgan's law. So part of the challenge here is we're trying to be very mechanical, very robotic about this. We're not trying to think ahead and understand or intuit why this would be equivalent to this. That's a really hard thing to do, and it's not useful in this context. What we're trying to do is very mechanically find a law of logic that gives us an equivalence of this with something else. Presumably something that's going to be easier to work with. So let's keep going. Is there a law of logic that lets me replace part of this with something else? Double negation, there we go. We have this involution law, not P is equivalent to P. So I can take this and I'm going to replace not P with just plain old P. I'm going to call that double negation. All right, you getting the idea? Need another law of logic. We want to change this into something else now. Got a proposition in this form, something ANDed with something else, ORed with yet something else. Distributive, perfect, right? We've got this law over here. P and Q or R is P and Q or P and R. So again, think of these as placeholders. This doesn't have to actually be P with a not in front of it. It's just something with a not in front of it. So distributive law, I'm going to make my box not P. I'm going to make my circle P. I'm going to make my triangle not Q. So the distributive law says this is equivalent to not P and P, or not P and not Q. Aren't you glad we have computers to do this for us? What if we don't? We got to do it ourselves. What can I do to this proposition down here? How can I simplify it? Not P and P is just true. It's funny, that's what I was thinking a second ago, but that turns out to be wrong. Not P and P is P and not P turns out to be equivalent to false. I don't know why I thought it was true also. So not P and P, we can replace that with false. And that's the negation law. Yeah, and or would be true. Exactly. All right. Now, our expression is getting simpler, so finding patterns may be a little easier. So what can I do with this expression? And I can use the identity law, which says anything ORed with false is just equivalent to anything. So this is equivalent to not P and not Q. That's the identity law. And so, hey, what have we done with all of this? We have proven that this is logically equivalent to that. And that's what we were trying to prove. We were trying to prove that's logically equivalent to that. Reminds me of trig. I shouldn't say that out loud, but yeah, I get that. So this is an example of a proof, right? It's a very rigorous demonstration of something, but the process of figuring out what to do in each of these steps, that is not rigorous at all. That's something that we need to kind of like think about and stare at and try things and eventually find something we can write that's going to hopefully help us. But the more you do this, the easier it gets. Eventually, you'll get to a point where anytime you see something like this, you're going to think De Morgan, right? If you see a conjunction or disjunction, you see a negation outside, your brain's going to say, use De Morgan's law. And you'll write that down. And anytime you see double, double, not P, you got to think P. Let's just use double negation. So this comes with practice. All right, so we'll come back to that and we'll spend some more time working with that idea of doing a proof. Let's switch gears for a moment. Let's talk about quantifiers. So different topic, but still in the area of making new propositions from old. All right. So we have two quantifiers. Um, we have something called the universal quantifier. And we write the universal quantifier as an upside down A, followed by some variable. And this we can translate as for all x. And so, for example, here's a proposition. For all x, x is bigger than 0 or x is less than or equal to 0. That's a proposition. It's a declarative statement. And that happens to turn out to be true. Every number is either positive or it's less than or equal to 0. For all x, x plus 1 is bigger than x. That's another declarative statement, and that also turns out to be true. For all x, x squared is bigger than x. Is that true or false?
False.
That's false. Why is it false?
1 squared is 1.
Yeah, 1 squared is 1. That's not bigger than 1. So proving things is false, you just got to find one counterexample. How about for all x, x squared is bigger than or equal to x? So 0 squared is bigger than or equal to 0. 1 squared is bigger than or equal to 1. 2 squared is bigger than or equal to 2. Negative 1 squared is bigger than or equal to negative 1. So this is true, but only if x is an integer. If x is the number 1/2, 1/2 squared is 1/4, that's not bigger than x. So when we say for all x, we need to know what's the universe of x we can choose from. Because this statement is false if we're working over real numbers. So when we say for all x, we need to know what the universe is. Now, it may be clear from context if we're doing something that involves integer, 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 and we make a statement for all x, it probably means integer. But if we just come on a blank sheet of paper and I say for all x, x squared is bigger than or equal to 0, depends on what the possible values for x are. Right, this is true for integers, this is true for reals. It's not true for complex numbers because I squared is -1. So we need to keep in mind the universe. All right, so that's the universal quantifier. The other one is the existential quantifier. And we write that as a backwards E. And that means there exists an X. Such that something. So for example, there exists an X, and I'll go ahead and put a universe down here. There exists an X contained in Z such that X squared is equal to X. So this is the proposition that there's an integer equal to its square. And that turns out to be true. It's true for 0 and it's true for 1. There exists an X in the integers such that X squared is less than X. And that's false. But there exists an X in the reals such that X squared is less than X. That turns out to be true. For example, X equals 1/2. So yeah, this is kind of the opposite, right? All you need to do is find 1 to prove that it's true. It's just saying there exists at least 1 where this is true. The universal quantifier is saying for all. So to prove it's true, you would have to show it for every possible X value, which is usually an infinite number of values. But to show it's false, you've only got to find 1 where it fails to be true. So they're sort of opposite workloads. All right, good. So we'll sometimes use these quantifiers with what we can think of as a family of propositions. And so a family of propositions is a collection of propositions that we can write typically using a variable. For example, let P of X, where X is an integer, be the proposition 2X is bigger than X. So X can be any integer, and for each possible value of X, we have a different proposition. For example, P of 5 is the proposition 2 times 5 is bigger than 5. P of -1 is the proposition 2 times -1 is bigger than -1. So this is defining an infinite number of propositions, but in a way that I can work with them without having to write an infinite number of things. So now I can make a new proposition which says something like for all X in the integers P of X. So this is the proposition that for all integers X, 2 times X is bigger than X. Which, as we noted previously, is false because 0 is an integer, but 2 times 0 is not bigger than 0. But if we said there exists an X in Z such that P of X, well, that's definitely true. For example, the integer 1, if X is 1, P of X is the proposition that 2 times 1 is bigger than 1. That's true. All right, got the idea? So let me leave you with one more notion, and then we'll call it good for today. We'll come back on Wednesday, backtrack a little bit, and then continue forward. Let me look at 2 examples. For all X contained in the set of natural numbers, P of X, And this really means that, for all x's in this set, p of x is true. So what are the x's in the naturals? Well, for example, 0 is a natural number, so p of 0 is true. And if I pick another natural number like 1, p of that number has to be true. And if I pick another natural number like 2, p of that has to be true, and so on. So this is just a really shorthand way of writing this infinite conjunction of propositions. And there exists an x in n such that p of x. Well, what does that mean? Can I expand that out in some way?
P of 0 or P of 1 or P of 2.
Oh, perfect. Right? It means there's some x in here where p is true. Well, what are the possible values? It's either p of 0 or p of 1 or p of 2, and so on. So this is a shorthand way of writing this infinite long disjunction of propositions. And this one's going to be a big part of our focus in about 2 weeks when we talk about mathematical induction. Okay, so that's another way to look at these quantifiers. Good. We're at a good stopping point. We will come back on Wednesday and we'll look at some other ways that we can put these quantifiers together and see how they interact. And then we're going to go on. We're going to start looking at logical expressions, what we call rules of inference, which is going to be the second part of the table from the text, which I already closed. But the bottom of page 50 in the textbook. All right, cool. Finish up the homework, submit those PDFs by Wednesday morning, and I will see everybody next time. Have a good rest of the day. It's getting sunny out. All right, see you all next time.
Yeah, on Wednesday. Thank you.
See ya.